Hello and welcome to this video where today we're going to be looking at the photoelectric effect. Now the photoelectric effect is something that happens if we have light and if we have a metal such as this. So if we take any bog standard metal, for example, I've got my pen, so for example this may well be a zinc sheet and we're looking at it side on. And the zinc sheet is a metal because, and one of the properties as we know of metals is that they contain free electrons. So all of these little dots are free electrons and they're delocalized, so they're free to move throughout this metal. They're not associated with any particular ion. And we could imagine that if we gave these free electrons enough energy, then what could happen is that the electrons would vibrate and they'd vibrate more and more, and eventually they'd be emitted out of the metal. So that's what the photoelectric effect is. If we shine light onto a surface, onto a metal surface such as zinc, then the light energy is absorbed by the electrons and the electrons are emitted out of the metal. And that's what's happened to this particular electron here. Now this electron here is given a special name. Because it's been emitted because we've shone light onto it, then it's called a photoelectron. So a photoelectron is simply just an electron that's been emitted because we've shone light onto a metal and it's gained enough energy to break its bonds that hold it to the metal, and it's been emitted. So scientists were really fascinated by this, and they did lots and lots of different experiments where they looked at different types of metals such as zinc, aluminium, sodium for example, and they looked at different frequencies of light, and they also looked at the intensity of light because they knew that intensity of light was a particularly important quantity. And then they tried to explain what was going on. So before we have a look and see what they thought, we just need to have a definition of intensity. So intensity is given by this expression here. Intensity is the amount of energy that hits a certain area every second. So we've got this light that's giving out light energy. It's hitting this area of the metal sheet, and the amount of energy that hits it per second is the intensity. And you could imagine that if, for example, if we took this metal sheet and we moved it closer to the light like this, then the energy is being absorbed by a much smaller area. And because it's been concentrated much more on this area rather than the whole area, then now we would say that the intensity of light has increased because it's basically being concentrated on a smaller area. So if we just put this back for a second, so that's basically what intensity is. It depends upon the amount of energy that's being absorbed, but also the area. So scientists thought, right, okay, we've seen what's going on. Let's try to explain it. So we know that light is a wave. So let's try to explain it using our wave theory, and intensity is a really big part of wave theory. So what they thought is, right, okay, we've got this energy that's constantly being given out, and the energy is spread out over this whole surface, and this part of the surface and this part of the surface, because the energy is spread out over all of it, every single bit of the surface receives the same amount of energy. So you could imagine that, for example, this electron here and this electron here that's inside the metal and this electron here that's inside the metal and so on are all receiving the same amount of energy. So they all start to vibrate more and more, and eventually they get to a point where they've gained so much energy that they vibrate so much that this one's emitted and then this one's emitted and this one's emitted. So all we have to do is shine a light on it and wait long enough, and these electrons will start to be emitted. And they thought, okay, that seems like a really, really good theory. The problem is that this didn't match up. Their theory of exactly what's going on didn't match up with what they saw. And if your theory doesn't match up with what you see, then your theory can't be right. So this is what they expected to happen. No matter what the frequency of the light, electrons should be emitted because we're shining energy onto this surface, and so because we're shining energy onto all of this surface, all of these electrons are going to gain this energy, and so eventually they'll start to have enough energy to break their bonds and be emitted. Also, if we increase the intensity, so we increase basically the amount of energy that we're providing to this surface, then the kinetic energy of these photoelectrons should also go up because we're giving them more energy, so they gain more energy, so they should move faster. What they actually saw though is that if we take this for example, this doesn't happen. What actually happens is that this effect only happens if we have light above a certain frequency. So you could shine low frequency light onto this particular metal for as long as you wanted, and these electrons would never ever ever be emitted. So this didn't work. They also found that the maximum energy does not increase with intensity. In actual fact, what the maximum kinetic energy does do is it increases with frequency. So if we increase the frequency of this light, then it increases the kinetic energy of these photoelectrons. If we do increase the intensity, what we actually see is that the number of electrons emitted goes up. So if we have a low intensity, only a couple of these electrons, for example, may be emitted. And we then turn the intensity up and lots more start to be emitted. So they had a real problem because they said, okay, light's a wave and this is what should happen, but this is actually what's happening. So what's going on? So they were baffled. This was one of those phenomena that they really couldn't explain. And it wasn't until the late 1800s when Max Planck came along and basically said, right, instead of light being a continuous wave, it comes in little packets, that people started to put two and two together and think, that's interesting, because that doesn't necessarily lead to these conclusions. And then in 1905, Einstein came along and basically said he took the theory one extra step. So what he said was this, and here basically is a reminder, this is basically what they saw. So this is a reminder of what they saw. So what he said is that instead of light being continuously given out and the energy being shared over the whole surface, the energy is given out in little packets. So it's given out in photons. So here's a little photon, and the photon travels along to the surface, and obviously it can't spread out over the whole surface. It's only going to hit, or only it's only going to interact with this part of the metal here. So it's only going to interact with this electron here. And what Einstein said is that one photon can only interact with one electron. So one photon only interacts with one electron. You can't have one photon interacting with two electrons or three electrons. It's only a one-to-one thing. So one photon interacts with one electron. And so he said, right, okay, so all of the energy of this photon can be absorbed by this electron. And we know from what we've seen before that the energy of a photon, E, is equal to hf, so the energy, and we've seen this in a previous video, so the energy of our photon is equal to Planck's constant, so is equal to Planck's constant, which you can look up in your data sheet, multiplied by the frequency of the light. So all of a sudden, this started to make sense, because instead of shining light on here for a long time, so if we have a low energy photon, the photon will come along, it'll interact with the electron, but it won't have enough energy to break the bonds. And so all that will happen is that this will start to vibrate a little bit more, it'll interact with the other particles, and so your bar will probably start to heat up just a little tiny bit. But if you've got a photon that's got enough energy, then it's got high frequency, then it will interact with this electron. It'll give this electron enough energy to break the bonds, and so this electron will therefore be emitted, and we will see a photoelectron being emitted. So that explains this. It explains why it only happens above a certain frequency. It happens above a certain frequency because we have photons, and the photons have a certain energy associated with that frequency. Also, we saw that excuse me, we saw that there was a maximum kinetic energy that was related to the frequency, not the intensity. Now, the intensity is basically now just the number of photons we see. So if we have a low intensity light, we just maybe have a few photons. And this is going to have no effect whatsoever on the kinetic energy of these things here, because they've all, if we assume that this light's all made up of the same frequency and the same photons, then all of these are simply just going to interact with one electron. They give the electrons the same amount of energy, and so if we have an electron that is on the surface, then all of the energy is basically given up just to break the bond and then to move away. If we take this photon and this interacts with an electron that's in the surface, then what this has to do is it has to give the electron enough energy to move through the metal, which is going to take some energy, and then it also needs to break the bonds, and then it will also have some kinetic energy. So this thing will have less kinetic energy than, for example, this electron here, because this hasn't had to use some of the energy to get away from deep inside the metal. So this will have a bigger kinetic energy than that, but there'll still be a maximum kinetic energy, because the maximum kinetic energy comes from a photon interacting with electrons that are just on the surface of the metal, electrons that don't have to take some of that energy to move through the metal first. However, if we increase the frequency, we increase the energy of these photons. If we increase the energy of these photons, then we're going to increase the maximum kinetic energy that we see. So that explains this as well. If we increase frequency, we get higher energy. If we get higher energy, we get higher kinetic energy of these emitted photoelectrons. If, however, we increase the intensity, we simply get more photons. And because we've got more photons, they can interact with more electrons. And so because they interact with more electrons, we see the number of electrons go up, which explains this here. So simply by thinking of light as being made of photons rather than a wave, it explains everything to do with the photoelectric effect. So really, this was the very, very first thing that said that light doesn't always behave as a wave, it can sometimes behave as a particle too. And that's why this effect is really, really, really important. It's evidence that light behaves not only as a wave, which we know it does sometimes because it reflects and it refracts, but it also can behave as a particle. And this is the first real evidence that we've got for that. So, there are a couple of key terms that we need to learn before we can move on. So this frequency at which this happens, so we said this will only happen above a certain frequency, and this frequency is called the threshold frequency. So if we have light, or if that has a certain frequency below the threshold frequency, then we won't see the photoelectric effect happen. When we get to the threshold frequency, then we will see the photoelectric effect happen. So this is important. There is a threshold frequency. This is the frequency at which we start to see the photoelectric effect. We can relate this to the type of metal. So, for example, if we take zinc, let's take zinc for example. Zinc has its own properties. It'll have its own, and because zinc is a certain type of metal, then it'll take a certain amount of energy for these to be able to break the bonds that hold it to the metal. Now, we know that if we just take a step back a second, we know that the energy of the photon is equal to hf. Okay, and this is the energy of the photon. It comes in, and some of that energy is used to break these bonds. Okay, so the minimum energy it's going to take to break this bond is equal to this, and we give the energy so the energy that it needs to break these particular bonds is given a special name. This is called the work function. And every single metal has got its own value of the work function. Simply the energy it takes to break all of these, to break the bonds that hold the electrons into the metal. So if you take zinc and you take, for example, aluminium, then zinc will have a work function, an energy it takes to break these electrons away from the metal, and aluminium will have a different one. Okay, so this is a characteristic of the type of metal that you've got. Now we can relate the work function, which is the amount of energy it takes to break this electron away from this, to the frequency that's needed for that to happen. So we know that energy is equal to hf, and we know that the energy needed to break the bond is equal to the work function, and the work function is given the symbol phi. Okay, then what must happen for this just to happen is that the hf, so the energy of the photon, must be equal to the work function. Okay, if the energy of the photon is bigger than the work function, then the electron will be able to break away, but also it means that it'll have some extra energy left over, and that will manifest itself as kinetic energy. Now, a very common question in an exam is to calculate the frequency at which this happens. So if, for example, you know the work function, and this needs to be measured in joules, it can't be measured in electron volts. So if you get a question where this is measured in electron volts, you need to convert it into joules. If you want to work out the frequency of light that's going to break the electron away from zinc, for example, you simply rearrange this equation. So the frequency of light needed would be equal to the work function divided by h. Okay, so you would take the work function measured in joules, you divide it by Planck's constant, and that would give you the frequency of light, and the frequency of light, as we know, is measured in hertz. So you can link the work function of a metal with the frequency of light. Now we can use this to actually write down something called Einstein's photoelectric equation. Okay, so we're still thinking about the same effect, and we can put a few things together now. So if we think about just photons, then we know that the energy of a photon, as we've written down many times, is equal to hf. So this is the energy of the photon, this is the frequency of the photon, and this is simply Planck's constant. Now if we think about it, if we shine a really high frequency or a really high energy photon onto here, and this, so for example, this electron here absorbs that, it's going to use some of that energy to break its bonds, so it's going to use some of that energy to release itself away from the metal, and any extra left over energy is going to be used as kinetic energy, so it's going to use that to basically move away from the metal. So the energy of the photon is split into two now. It's the energy to release itself, which is basically our work function, plus the kinetic energy that it's got when it's moving away. So we write that like this. So the energy of the photon, which is equal to hf, is now equal to the work function plus the kinetic energy of our photoelectron. So the energy that we start off with is conserved. So this energy that we start off with is equal to this energy, but it's now split into two. It's been used to break the bonds, and any extra energy left over has been used as kinetic energy to move away. Now you know from GCSE that the kinetic energy is equal to a half mv squared, where m is the mass, and if we're thinking about electrons, that'll be the mass of an electron, and this is the velocity, so how fast the thing's going, and that's our kinetic energy again. So if we look at this, we can simply put this into here, and we end up with our final equation. So this is Einstein's photoelectric equation, which links the frequency of a photon to the work function and the kinetic energy. So you could, for example, you can be given lots and lots of different types of questions. You could, for example, be given the frequency of the light, the work function of a metal, and you could be asked to work out how fast the photoelectron's going, because this you can just look up on your data sheet, this will be given in the question, and this is a frequency. So as a reminder, frequency is measured in hertz, our work function needs to be measured in joules, mass is measured in kilograms, and the velocity is measured in meters per second. Okay, so you could be given lots and lots of different ways around to actually work this. You could give the frequency, the speed, and also the mass, and be asked to work out the wave function, for example. There were lots of different permutations. One particularly interesting thing, though, is that we can take this and we can rearrange it. So actually we'll work with this one a little bit. So we'll change colour, and we're going to rearrange this. So we're going to forget this E. So we've just got hf equals phi plus ek. So the energy of the photon is equal to the work function plus the kinetic energy. And if we rearrange it, we'll rearrange it like this. So the kinetic energy is simply equal to hf minus phi. Well, you might ask why I've done that. Well, it's easy in an experiment to alter the frequency of light that you're shining onto the metal, and then, or at least it's fairly easy, and then calculate or measure the kinetic energy of the photon, of the photoelectrons that are given off. And so this is our independent variable, this is our dependent variable, and so we could plot a graph. And if we plot a graph, then this will be our y, mx, oops, sorry, we'll make this slightly neater-ish. Okay, so y equals mx plus c, and if we look at that, we know that that's the equation of a straight line. So if we plot a graph where we put the kinetic energy on the y-axis, we have the frequency on the x-axis, then we should end up with a gradient that's Planck's constant and an intercept on the y-axis, which gives us the minus of the work function. And to be honest, that's exactly what we see, because if we move this away, if we were to do this experiment, we would see a graph like this. So we've plotted the kinetic energy against the frequency. We've changed the frequency, so we've started with a low frequency and we've measured the kinetic energy. So for low frequencies, we don't see anything happening at all. But then once we hit the threshold frequency, then we start to see, we can start to measure the kinetic energy. And the bigger the frequency, the bigger the kinetic energy. So as frequency is increased, then kinetic energy is increased. If we read this number off, this gives us our threshold frequency. And if we extrapolate this line back, then we end up with this here giving us the work function. There is a different way to do it. You could, for example, you could just read the threshold frequency off here and then use what was on the last slide to work out what the work function is. But this is just an easy way to work out the work function straight away. So the question then comes, if we do this, for example, for our zinc, yeah, what would it look like then if we took a different metal that had a higher threshold frequency? And this is again is a common exam question. So, and they very often give you a graph like this and simply say, draw on here a metal has a bigger threshold frequency. Draw the line you would expect to see on this graph. And if you do that, then you would expect to see this. And there's a couple of key points really. What is important is that the gradient's always the same. So the gradient is always equal to h. Okay, so the gradient of this graph is always equal to Planck's constant. It's never any different. So you would get a different set of parallel lines, but they have a different threshold frequency. The threshold frequency for our first metal is here. The threshold frequency for our second metal, you could read off from here. Okay, and again, you can extrapolate this back, and you would end up with a different work function. But what's important is the gradient is exactly the same. So just to summarize, what we've seen is that if we shine light onto a metal, then we can see an effect called the photoelectric effect, where electrons are emitted by the metal. And this was the first real proof that light behaves like a particle rather than just a wave, because it contradicted what wave theory should say. We then had a very quick look to see what the work function was, and we had a look at Einstein's photoelectric equation, which is this thing here. Which are expected using lots and lots of different ways. So there are lots of questions that you can go away and actually look up. And then finally, we looked at what happens if you do an experiment where you change the frequency and measure the maximum kinetic energy. If you do that, you end up with a gradient that's Planck's constant, and you can read off the threshold frequency straight away, and you could extrapolate this back to work out what the work function of a metal is. So that's me done for today. Thank you very much for watching, and I will see you again soon.